Hello and welcome to our video on our major qualifying project. The members include Rishi Gupta and Brendan McLaughlin, and our advisor is Dr. Zong. Our project was on the investigation and quantification of ceramic powder stickiness. This video will primarily discuss the problems and issues that arose through the project, how we resolved them, and what improvements could be made in future projects, with relevant background information where appropriate. We wish to briefly discuss some essential background of the project and what our main goals were. Ceramics occupy a unique role amongst materials as seen here. This necessitates a processing approach involving the ceramic powder in a binder called a green body. After forming, the binder is burned out and then the part is sintered for its final properties. While this is generally a sound system, there is a significant problem in pressing the green body. The powder might not fully eject and instead stick to the walls of the die. In a fast automated assembly line, this error can cause significant setbacks and potentially ruin large batches of a part. There are currently only stopgap solutions, and so finding a way to quantify this stickiness was a key goal for this project. Our primary investigations were to look at the glass transition temperature of the binder as the leading cause of sticking. There were several factors to investigate shown on this slide. We focused primarily on the first three significant points: the number of pellets, the temperature of the die, and the composition of the binder package. The humidity was challenging to account for and more difficult to control. It is arguably one of the more significant influences on powder compaction and should be explored more thoroughly in future projects. Small changes in humidity can have a considerable effect on the binder package and may have affected some of the results in unforeseen ways. This slide breaks down the composition of the powder and binder that were used in pressing. An important note is the difference between the powder preparation processes in this project versus the industry. The industry uses a spray-dried powder which is optimal for pressing. The powder created by us was inconsistent as it had to be ball milled, pan-dried in an oven, and finally ground down further by a mortar and pestle. Additional water even needed to be added to aid in homogeneous mixing. It is possible that the differences in method had a significant influence on the results. Comparing this to some pellets of industrially sprayed dried powder would be beneficial in determining if powder preparation had any impact on pressing results. This flowchart is a brief explanation of the processes in creating the powder and pressing the pellets. There are essentially two preparations, one for just the binder package and the other is for the ready-to-press powder. These images show the die and press that were used in this project. The pressing rods and sleeve form a cylindrical volume where the powder is poured and pressed into a pellet. There were a few problems that occurred with the die. The first was the difficulty in removing the different parts to load up the following sample. Usually after 7 to 8 samples, it would be difficult to remove by hand, requiring excessive force from tools or cleaning the die. Since the die isn't rated for more than one press before cleaning, a different one might have fixed the issue, something to consider for future projects. On the other hand, industrial applications would have much better means for separating the die than human muscle power. Die wear would also occur from this, further exacerbating the issue. Excessive force from tools also damaged the dies further, and this may have impacted the tolerances, causing less or more powder leakage. Overall, the die was complicated to work with for extended periods of time when not cleaned properly. When we initially started pressing pellets, there were defects present in a large percentage of the pellets. The pressing parameters were the most likely suspect for creating these defects, so some experiments on the densification of the powder were performed. The results of this are detailed next. The important takeaway from the graph is that the initial pressing parameters used were very excessive. There was a minimal increase in density, but a large increase in pressure. Lowering both of these values produced completely defect-free pellets, as seen previously. When investigating the binder package, separate batches of the binder had to be specifically made. These were done similarly to the ready-to-press powder discussed earlier. A major difficulty was working with very small amounts of the individual components. It was challenging to measure hundredths of a gram worth of liquid, or even smaller amounts for the final samples. The solution we found was to create large batches of the liquid that were much easier to measure once we were confident we had enough raw materials to not run out for future testing. This slide breaks down the setup for heating the die for elevated temperature testing. The die was fitted with a band heater which was connected to a solid-state relay. The relay was responsible for regulating the current and voltage from the PID controller to the band heater. The thermocouple was supposed to measure the current temperature and turn the band heater on when it was below a target value. There are several problems with this setup that will be explained next. The temperature testing had the most issues and would be a great starting point to improve upon in future projects. First, the setup did not work as intended, as mentioned earlier. The band heater, which was to heat the die, did not snugly fit. It was about ½ an inch larger in diameter. Furthermore, either the controller or thermocouple did not work as intended. This meant that accurately controlling the temperature was extremely difficult. Ideally, the thermocouple would report the temperature, and when the target temperature is reached, the controller would turn off the band heater. This would stabilize the temperature around the target temperature. The stopgap solutions implemented were to use an infrared thermometer to measure the temperature on the outside of the die and manually control the band heater by bypassing the thermocouple and controller. This led to several issues that could not be fixed. There was no way of knowing the temperature of the inside of the die where the powder was located. There was also wasted time if the temperature overshot, as it took much longer to cool the die than to heat it back up again. There was also a surprise when the temperature was 55 degrees C, and initially it was assumed to be due to higher humidity. However, when tested again at lower humidity, the pellets lost even less mass, meaning it is most likely another factor. Identifying and isolating any of these factors would be highly beneficial in future research. In conclusion, although we were unable to quantify ceramic powder stickiness, this project was successful in preliminary testing of factors that contribute to powder stickiness in the die. However, there is much room for improvement. Determining practical methods in separating the die, either by hand or with assistance, would help allow for extended usage and a larger buildup of residual powder to examine. Furthermore, finding a more appropriate die, if possible, would help eliminate powder loss through tolerances. Utilizing a baseline spray-dried powder for comparative testing of the powder preparation could indicate if different powder preparation methods should be further investigated, and if powder composition could be more significant using alternative methods. Having appropriate and working equipment for the elevated temperature testing would have made measuring the temperature highly consistent, and exploring ways to control humidity and perform testing under specific conditions would also be helpful specifically for this binder package. The most important takeaway for future projects is tightly controlling each of the variables and acquiring more reliable and useful equipment if possible. Finally, we would like to thank several people who are instrumental in this project. Our advisor, Professor Yuzong, for his guidance, feedback, and support through this project, Tawny Tambaleo for her assistance in the lab and prior knowledge on this project, Ray Wang for his instruction on proper operating procedures and for the equipment, and Adam Stevenson from St. Gobain, who provided raw material samples and industrial expertise to the project. Thank you all for your assistance in this project.